Oh, hi there. How's it going? In case you didn't get it from the intro video, I am not going to give a standard voiceover talk where we have some slides and then we go over I narrate through the slides as I would do in a standard presentation. We're going to have a little bit more fun. Any feedback on this type of talk would be appreciated because, as I mentioned, it's an interesting year. And so it's a good excuse to try something new, I thought. Okay, and as you saw in the prologue, what we're going to talk about today are nonlinear processes on networks. Let me tell you about a little bit more about what I mean by that. Okay, now one other note for all you folks over here. It's pretty bad form to introduce something by telling you what it's not as opposed to what it is. So to cut through the chase here, what I mean by a nonlinear process on a network is simply we're going to take a linear process on a network and just throw a small nonlinear function on it somewhere. It could be a power function like x to the 1/2, or it could be a log transform or a tangent or something, but we're not talking about massively changing the linear structure that you're used to. We're just adding a little bit of a tweak to it. Linear processes on graphs are probably something that you've run into before. And for a variety of reasons, one of my favorite examples of this is the PageRank process. The way I like to think about PageRank is as a process that takes information from a seed set of vectors and moves it across the graph onto all of the vertices or nodes of the graph. That is, it takes the information from the seeds and diffuses them across the entire network. Now, we usually think of PageRank as starting with a set of seeds and moving that information across the graph, but you could use any non-negative vector of information, weighted, anything else that you want to put in there, and the mathematics of PageRank largely go through for that as well. PageRank, of course, is a linear operator. And so what that means is if you have a linear combination of seeds, you get a linear combination of PageRank vectors. And we can write that in a couple of different ways. We can write it mathematically, or we can just draw a picture of it. Now, linear operators are really awesome, and they've been responsible for a tremendous success of research in graph theory and different ideas in network analysis. And one of the reasons for that is linear operators really exist at the nexus of a whole lot of different ideas. We can derive or state PageRank from a number of different perspectives. It's from Markov chain theory, from dynamical systems theory, from smooth functions on graphs, from matrix function theory, from a maximum likelihood estimate on stochastic block models, and many, many, many more. There are continually new perspectives on PageRank that emerge, and this single algorithm exists at the nexus of all of them. When you think of a PageRank algorithm, you can think of just running the simple linear diffusion from seeds to solutions, but implicitly what you're doing there is you're running a whole host of different algorithms, all of which have slightly but closely related interpretations. So why am I spending all of this time talking about linear processes on graphs when the title and the subject of this talk is on nonlinear processes on graphs? Well, the reason I mention all of this is because when you apply a small nonlinearity to any of these derivations, all of those equivalences break. So when we talk about nonlinear processes on graphs, we need to start from one of those different perspectives and put the nonlinearity in a natural place in that perspective. If you apply a small nonlinearity, say take a power iteration that's been inspired by Markov chains, and just apply a small square root function at every step, then we lose the vast majority of those equivalences. What this means is when we do these nonlinear processes on graphs, it's important to fix ourselves in one of those many different interpretations of PageRank and apply that nonlinearity in a way that makes sense for that particular interpretation. What I'm going to tell you about today are a few of the ideas we've been working on in this space, where we'll take one of the interpretations of a linear process on a graph, case in point, PageRank, and then we're going to apply a small nonlinearity at some point. And we're going to see some of the trade-offs and advantages that result from that transformation. This involves a whole bunch of projects I've been working on with some very talented students recently. I really wish the students could be here to tell you about this themselves, but it's not as easy as it might seem. A lot of them are away on internships and other types of activities right now. Let me also reiterate that there's others working in this space too, including some of the mini symposium organizers. In a project on nonlinear diffusions with Rania Ibrahim, what we did was we took a dynamical systems perspective on some of these graph diffusion processes, and we just put a little p-norm or a p-Laplacian function as the transfer function. Essentially, we put this into the derivative function of the dynamical system underlying these diffusions. And what this allowed us to do was to get a lot more interesting results that was competitive or actually exceeded some of the performance of neural network models or some of these graph convolutional networks that people had developed. In the glance method with Huda Nassar, Shweta Jain, Caitlin Kennedy, and Austin Benson, what we did was we took a nonlinear transformation of the adjacency matrix itself, and then we did a whole bunch of spectral methods. Now, the inspiration here actually came out of some work that's in our hypergraph methods, where you use a clique expansion of a hypergraph in order to do things. What we did in the glance method was we did exactly that, but we sort of viewed this as a nonlinear transform of the adjacency matrix. And so we were able to put in a set of custom weights that wouldn't have followed exactly from what the hypergraph methods would have suggested. This just gave us a number of opportunities to develop a visualization algorithm that makes nice looking pictures of graphs. We then demonstrate this by showing that the pictures of graphs that we identify have different trade-offs with respect to which ground truth topological properties they preserve compared to other ways that people have drawn pictures of graphs before. In one of the other projects we've been working on recently with Kimon Fontalakis, Meng Lu, and Michael Mahoney, what we've done is we've taken a look at all of the literature on minimum cut and maximum flow based cluster improvement. Now in max flow min cut cluster improvement, what you do is you start from a reference graph and you improve it into an improved cluster S. And we'll see some examples of this in one of the future videos. But you can relate that back to you can actually derive PageRank-like methods from taking that same methodology and applying a 2-norm operation somewhere. The min-cut max-flow operations correspond with a 1-norm version of that same type of methodology. Now, one of the things that we struggled with that min-cut max-flow technology is that the output is always discrete from that. You always get a 0 or a 1. Whereas with linear operations like PageRank, what you get is a real valued vector that allows you to sort the values meaningfully. It allows you to threshold at various levels. It allows you to study gaps in those vectors and all sorts of other useful things when you're talking about downstream applications. One of the things we like about the spectral methods is that you can do little local visualizations of the network. You can meaningfully use either eigenvectors or PageRank vectors in order to get local embeddings of the nodes. Using these flow techniques, we didn't see a way to do that. However, what we figured out was that you can use a sort of randomized or expectation perspective on what you get out of a PageRank vector, and then you treat this as a process from input to output, and you use an SVD, and you can get a lot of similar things from these discrete 0-1 vectors that give you a very different style of visualization for a local part of a network. just to cut to the chase, it tends not to look at the manifold structure like you get out of the two-norm spectral methods. What it really does is it preserves cluster structure. So if you think that your graph has a lot of sub-cluster structure, this might be far more appropriate than some of the manifold structure methods based on PageRank. In another project that sort of naturally follows from the flow-based one, and this is with Meng Lu, what we did was we said, okay, well, if PageRank corresponds to a 2-norm problem and these max flow min cut problems corresponds to a 1-norm problem, there's a family of things in between that are based on p-norms. And using those, we can get all sorts of really neat algorithms that have some of the advantages of the flow methods. That is, one of the classic things that the flow methods do better is they track boundaries much more sharply than the spectral or two-norm methods do. But one of the challenges with the flow-based methods is that they have trouble expanding from a single seed node. So in general, the flow-based methods need a really large region of the graph to refine. And that's actually due to some of the downsides to the flow-based theory. But what you can get with these p-norm methods is actually something in between. And we've actually been able to come up with a whole host of different algorithms that are really neat, simple generalizations of PageRank style algorithms, but that apply to these nonlinear p-norm functions as well. If you're familiar with something called the Anderson-Chung-Lang push method for personalized PageRank, or you simply sort of understand what Gauss-Seidel would do on a coordinate basis for solving a PageRank vector, what we can do is we can solve these p-norm diffusions. We just change the simple closed form update into a bisection search instead. Now, so far we've just seen a teaser over some of these results. There are definitely some challenges with using these different methods, and it's by far from a solved problem. The algorithms have different types of trade-offs. Parameters may be easier or harder to set depending on how you do it, so it's definitely a space where we need better ideas. And let me just say that the linear graph algorithms out there are actually really good, so they make a hard benchline or baseline to compete again. The key thing with all of these nonlinear methods, though, is we don't get trivial combinations of seeds. Or sorry, simple linear combinations of seeds. All of these have the property that linear combinations do not give us linear combinations of the output. This is going to offer us some interesting opportunities, and so we're going to investigate those over another set of videos. So if you're interested in talking more about these, please let us know and we'd be happy to chat more.